the theory of plate tectonics stands as a cornerstone of modern geology, reshaping our understanding of Earth's dynamic history. This revolutionary concept has revealed the ever-changing tapestry of our planet, where continents collide and oceans expand. As we embark on this journey, get ready to uncover the ancient secrets hidden beneath our feet. In the early 16th century, the German cartographer Waldseemüller created a world map that would change the way people understood the Earth's geography. This map, known as the Carta Marina, depicted the New World, which had been recently discovered by European explorers. As scholars and scientists studied this map, they began to notice something peculiar. The eastern coast of South America and the western coast of Africa seemed to fit together like a puzzle. This observation sparked a series of questions about the Earth's history and the movement of its landmasses. One of the earliest recorded ideas about the movement of the Earth's crust can be attributed to the French naturalist Georges-Louis Leclerc, Comte de Buffon. In his book Histoire naturelle, published in 1749, Buffon proposed that the Earth's continents had once been connected by land bridges, which had since sunk into the ocean. Although his idea was not widely accepted at the time, it laid the groundwork for future theories about the Earth's geological history. As the 19th century progressed, scientists began to notice other peculiarities about the Earth's geology. The British geologist Charles Lyell, in his influential book, Principles of Geology, published in 1830, described the concept of uniformitarianism, the idea that the Earth's geological features were shaped by slow, continuous processes that had been occurring over millions of years. This idea challenged the traditional view of catastrophism, which held that the Earth's features were shaped by sudden, violent events. Meanwhile, in the mid-19th century, the German geographer Alexander von Humboldt was studying the geography of South America. He noticed that the Andes mountain range was not a single, continuous chain, but rather a series of parallel ranges that had been formed by the uplift of the Earth's crust. This observation led him to propose that the Earth's crust was dynamic and that mountains were formed by the movement of the Earth's interior. As scientists continued to explore the Earth's geology, they began to notice a pattern of similarities between different continents. The Scottish geologist James Dwight Dana, in his book Manual of Geology, published in 1863, described the concept of accidental similarities, the idea that similar geological features on different continents were simply coincidental. However, other scientists, such as the Austrian geologist Eduard Suess, began to propose that these similarities were not accidental, but rather evidence of a shared geological history. Suss's work on the geological history of the Alps led him to propose the concept of Gondwana, a supercontinent that had once connected Africa, South America, and Australia. He published his ideas in a series of papers, including Das Antlitz der Erde, or The Face of the Earth, which laid the foundation for modern theories of continental drift. Although Suss's ideas were not widely accepted at the time, they marked an important turning point in the development of the theory of plate tectonics. As Suess's ideas about Gondwana began to gain traction, another key figure emerged to further develop the concept of continental drift. Alfred Wegener, a German meteorologist and geophysicist, became fascinated with the similarities between the continents and the Mid-Atlantic Ridge, a vast underwater mountain range that runs down the center of the Atlantic Ocean. In 1912, Wegener proposed that the continents had once been joined together in a single supercontinent, which he called Pangaea, and that they had since drifted apart. Wegener's theory was based on several lines of evidence, including the fit of the continents, the similarity of rock formations and fossils on different continents, and the presence of coal deposits and glaciated rocks in areas that are now tropical. He also noted that the Mid-Atlantic Ridge was characterized by numerous earthquakes and volcanic activity, suggesting that it was a zone of intense geological activity. Wegener's ideas were presented in his book, Die Entstehung der Kontinente und Ozeane, or The Origin of Continents and Oceans, which was published in 1915. Although Wegener's theory of continental drift was initially met with skepticism, it sparked a lively debate among geologists and other scientists. One of the key challenges to Wegener's theory was the lack of a mechanism to explain how the continents could have moved. Wegener proposed that the continents were able to move due to the convection currents in the Earth's mantle, but this idea was not widely accepted at the time. In the 1920s and 1930s, several scientists began to investigate the properties of the Earth's mantle and the potential for convection currents to drive continental movement. One of these scientists was Harold Jeffreys, a British geophysicist who argued that the Earth's mantle was too rigid to allow for the kind of convection currents that Wegener had proposed. However, other scientists, such as the British geologist Arthur Holmes, began to develop new theories about the Earth's mantle and its potential role in driving continental drift. Holmes, in particular, made significant contributions to the development of the theory of plate tectonics. In his 1929 paper, Radioactivity and Earth Movements, Holmes proposed that the Earth's mantle was able to flow over long periods of time, allowing for the continents to move. He also suggested that the heat generated by radioactivity in the Earth's core could be the driving force behind convection currents in the mantle. Although Holmes's ideas were not widely accepted at the time, they laid the foundation for later research on the Earth's mantle and its role in plate tectonics. As the 1940s and 1950s unfolded, the concept of continental drift continued to gain traction, with an increasing number of scientists contributing to the growing body of evidence. One such scientist was Maurice Ewing, an American geophysicist who had been studying the ocean floor and its properties. In 1947, Ewing began a series of expeditions aboard the research vessel Atlantis, which would take him to the mid-Atlantic ridge, where he would gather crucial data on the oceanic crust and its relationship to the continents. Ewing's work built upon the earlier research of Alfred Wegener, who had proposed that the mid-Atlantic ridge was a zone of intense geological activity. Ewing's team used a combination of seismic surveys, gravity measurements, and magnetic profiling to map the ocean floor and gather data on its structure. Their findings revealed a vast mountain range running down the center of the Atlantic, with a central valley characterized by high levels of seismic and volcanic activity. Meanwhile, in the UK, a geologist named Stanley Runcorn was working on the problem of paleomagnetism, which involved studying the orientation of magnetic minerals and rocks to reconstruct the Earth's magnetic field in the past. Runcorn's work showed that rocks from different continents had similar magnetic signatures, suggesting that they had once been joined together. This evidence provided further support for the theory of continental drift and helped to establish paleomagnetism as a key tool in the development of plate tectonics. In the 1950s, another American geologist, Harry Hess, began to develop a new theory about the nature of the oceanic crust. Hess proposed that the ocean floor was being created at mid-ocean ridges, where magma from the Earth's mantle was rising to the surface and solidifying into new crust. This process, known as seafloor spreading, would eventually become a central component of the theory of plate tectonics. Hess's work built upon the earlier research of Ewing and others, who had shown that the mid-Atlantic ridge was a zone of intense geological activity. His findings revealed a pattern of symmetrical magnetic stripes on either side of the mid-ocean ridges, which he interpreted as evidence of seafloor spreading. As the evidence for seafloor spreading continued to grow, scientists began to develop new theories about the mechanisms driving continental drift. One such scientist was Marie Tharp, an American geologist who had been working with Bruce Heezen to create detailed maps of the ocean floor. Tharp's work revealed a complex pattern of mountain ranges, trenches, and fracture zones, which she interpreted as evidence of a dynamic and constantly moving Earth. As Marie Tharp's work continued to reveal the complexities of the ocean floor, her maps became a crucial tool for scientists studying the Earth's crust. One such scientist was Frederick Vine, a British geologist who had been working with Drummond Matthews to study the magnetic properties of rocks on the ocean floor. In 1963, Vine and Matthews published a paper in which they proposed that the symmetrical magnetic stripes on either side of mid-ocean ridges were evidence of seafloor spreading, and that the Earth's crust was being created at these ridges as magma rose from the mantle and solidified into new crust. Vine and Matthews' work built upon the earlier research of Harry Hess and others and provided a key piece of evidence for the theory of plate tectonics. Their papers sparked a flurry of interest in the scientific community, and soon researchers from around the world were studying the magnetic properties of rocks on the ocean floor. One such researcher was Lynn Sykes, an American geologist who had been working with Jack Oliver to study the seismic activity of the Earth's crust. In 1965, Sykes published a paper in which he presented evidence that earthquakes occurred at transform faults, which were areas where two tectonic plates were sliding past each other. Sykes' work provided further support for the theory of plate tectonics and helped to establish transform faults as a key feature of the Earth's crust. As researchers continued to study the Earth's crust, they began to develop a more complete understanding of the processes that shaped our planet. One such researcher was Jason Morgan, an American geologist who had been working with Dan Mackenzie to study the movement of tectonic plates. In 1968, Morgan and Mackenzie published a paper in which they proposed that the Earth's crust was divided into several large plates that were in constant motion and that these plates interacted at their boundaries to produce earthquakes, volcanoes, and mountain ranges. Morgan and Mackenzie's work provided a major breakthrough in the development of the theory of plate tectonics and helped to establish the framework for modern plate tectonics. Their paper sparked a new wave of research into the Earth's crust as scientists sought to understand the complex interactions between tectonic plates. One such researcher was Tuzo Wilson, a Canadian geologist who had been working with other scientists to study the geological history of the Earth's crust. In 1965, Wilson published a paper in which he proposed that the Hawaiian Islands were formed by a hotspot, a zone of molten rock that rose from the mantle to the surface, producing a chain of volcanoes as the Pacific Plate moved over it. As Tuzo Wilson's hotspot theory gained acceptance, it helped to further solidify the concept of plate tectonics, and researchers began to apply this new understanding to explain a wide range of geological phenomena. One such researcher was John Dewey, a British geologist who had been studying the geological history of the Himalayan mountain range. In 1969, Dewey published a paper in which he proposed that the Himalayas were formed as a result of the collision between the Indian and Eurasian plates, providing a dramatic example of the power of plate tectonics to shape the Earth's surface. Dewey's work built upon the earlier research of Wilson and others, and helped to establish the Himalayan orogeny as a key example of continental collision. As researchers continued to study the Himalayas, they began to develop a more detailed understanding of the processes that had shaped this mountain range over millions of years. One such researcher was Peter Molnar, an American geologist who had been working with Paul Taponnier to study the geological history of the Tibetan Plateau. In 1975, Molnar and Taponnier published a paper in which they proposed that the uplift of the Tibetan Plateau was caused by the collision between the Indian and Eurasian plates, providing further evidence for the role of plate tectonics in shaping the Earth's surface. The work of Dewey, Molnar, and Taponnier helped to establish the Himalayan orogeny as a key area of research in the field of plate tectonics, and researchers from around the world began to flock to the region to study its geology. One such researcher was Roger Bilham, a British geologist who had been working with Vinod Kumar Gar to study the seismic activity of the Himalayan region. In 1979, Bilham and Gower published a paper in which they proposed that the Himalayas were still rising by about 1 inch per year, providing further evidence for the ongoing process of continental collision. As researchers continued to study the Himalayas, they began to develop a more detailed understanding of the complex interactions between the Indian and Eurasian plates. One such researcher was Simon Klemperer, an American geologist who had been working with Larry Brown to study the geological history of the Tibetan Plateau. In 1985, Klemperer and Brown published a paper in which they proposed that the Tibetan Plateau was underlain by a thick crust that had been formed as a result of the collision between the Indian and Eurasian plates, providing further evidence for the role of plate tectonics in shaping the Earth's surface. The work of Klemperer, Brown, and others helped to establish the Tibetan Plateau as a key area of research in the field of plate tectonics, and researchers from around the world began to study its geology using a wide range of techniques. One such researcher was Annie Cazenave, a French geophysicist who had been working with Bernard Minster to study the gravitational field of the Tibetan Plateau. In 1995, Cazenave and Minster published a paper in which they proposed that the gravitational field of the plateau was consistent with a model of crustal thickening caused by the collision between the Indian and Eurasian plates, providing further evidence for the role of plate tectonics in shaping the Earth's surface. One such researcher was Eric Calais, an American geophysicist who had been working with Simon McCluskey to study the seismic activity of the Himalayan region. In 2001, Calais and McCluskey published a paper in which they proposed that the Himalayas were still rising by about 1 inch per year, and that this process was accompanied by significant seismic activity, providing further evidence for the ongoing process of continental collision. As the 21st century progressed, researchers began to develop new technologies and methods for studying the Earth's surface, including satellite-based measurements of crustal deformation and seismic tomography. One such researcher was Michael Steckler, an American geophysicist who had been working with Leonardo Sieber to study the geological history of the Himalayan region using satellite-based measurements of crustal deformation. As the field of plate tectonics continued to evolve, researchers began to develop new theories and models for explaining the complex interactions between the Earth's lithosphere and mantle. One such researcher was Paul Tackley, a Swiss-American geophysicist who had been working with Antoine Rosel to study the geological history of the Earth's mantle using numerical simulations. In 2015, Tackley and Rosel published a paper in which they proposed that the Earth's mantle was characterized by a complex pattern of convection cells, providing further evidence for the role of plate tectonics in shaping the Earth's surface. The work of Tackley, Rosel, and others helped to establish the field of plate tectonics as a major area of research in the earth sciences, and researchers from around the world continued to study the complex interactions between the Earth's lithosphere and mantle. The ongoing process of continental collision in the Himalayan region remained a key area of research, with scientists continuing to study its geology using a wide range of techniques. The theory of plate tectonics has revolutionized our understanding of the Earth's dynamic surface, transforming the field of geology and shaping our perception of the planet's history. Thank you for joining me throughout this historical journey. That's all for today's History with Herodotus. Remember to like, share, and subscribe. And until next time, remember that, to understand the present, we must first understand the past.